In this sequence of videos, we are going to talk about some methods that we can employ to advance the k-means algorithm that we've discussed previously. In particular, we're going to talk about ways to assess the quality of a clustering that we've converged to through the k-means process, and we'll be talking about how we actually go about selecting that k value instead of just assuming that that's something that we know. So first and foremost, let's talk about assessing cluster quality. So one thing that we saw in the last lesson was that our k-means algorithm doesn't always converge to the same clustering, especially when we're picking these starting points at random. Shown here are 3 different clusterings with 3 cluster centers that we could converge to with the exact same data set. And clusters 2 and 3 are very close here, so I've just circled the slight difference between the 2 clusters, other than the color attribution of the clusters as well. So one question that might arise is which clustering is the best? Now, of course, that might depend on the context in which you're applying this algorithm, but if we're speaking most generally, there's one thing that we tend to do with clusterings to determine which one is the best, and mostly that's the one with the tightest clusters. So to be a little bit more specific, we discuss what's called the heterogeneity of a cluster. So in all of this, we're assuming that we've run our k-means algorithm and we're assuming that it has converged to a clustering. And so what we found are these cluster centers, Z1 through ZK. And then we also have these clusters, which are the chunks of observations that are attributed to that cluster center. So referring back to the previous page, our cluster centers would be the centers of the regions, and these x1 through x3s would be the different colors of the observations in that picture. In what I have written on this slide, I'm going to talk about having a distance function d to be totally general. However, the distance function that we've been using is the square of the Euclidean distance. So Euclidean distance is a very natural and comfortable distance metric. However, just like we've seen in previous data science techniques, squaring that distance measure doesn't really correspond to a loss of information, and it's much easier to deal with because square roots are something that are complicated to work with mathematically. So we're going to deal with the square of the Euclidean distance metric. And when we are computing these cluster centers, what we're finding is actually the centroid, or the center of mass, of that cluster. When we find this cluster center, we're finding something that minimizes that total distance metric within the cluster. That's how we go about computing that cluster center for that cluster. All we're doing when we introduce a measure of heterogeneity is we sum up all of the distances to center for all of the different clusters. The formula for that looks a little bit complicated, but here's what we're doing. The xi's are our clusters, the zi's are our cluster centers. This inner term of the sum right here is computing using whatever distance metric we're focused on. Here it's the Euclidean distance squared. For each cluster, compute the total distance from each observation that's in that cluster to the cluster center. The outer term of the sum is just adding all of those things up. So when we create that cluster center, we're focused on this inner sum and focused on making that as small as possible. But then what we want to do is add each of those things up and see overall, did we make one cluster very tightly bound at the expense of maybe making another cluster very sparse? And overall, that would be a bad thing. So what we're going to do is look at this heterogeneity, and we're going to define the strength of a cluster as to how large its heterogeneity is. So when we're looking for good clusters, we want them to have a very small heterogeneity. So if we look to minimize this function, any clustering that minimizes this function is going to be considered a very good cluster attribution, and any clustering that makes this value large is going to be considered less than optimal, even though it was something that our k-means algorithm brought to our attention and converged. Now, just to give you a little bit of a visual with that, I'd like to go back to the examples that we saw before, and I'd like to see how we take heterogeneity into account in our program. One thing that we can do to deal with the fact that k-means might converge to several different clusterings for the same set of data, and how do we know which one is the best one? One thing we could do is run our k-means algorithm several times, and we might get very different outcomes. But what we can do is measure the heterogeneity of each of the different clusters, and we can return the one that has the least heterogeneity as the best one to represent our data set. If you take a look at these examples that we have here, and we add the centroids for each of the regions, what we're doing when we compute that heterogeneity is we're computing all of these little distances that I've drawn in these pictures. For each observation, we compute the distance from that observation to the center of that particular cluster. So those terms in the sum, here are k is equal to 3. The terms in the sums would be 1, 2, 3, 1, 2, 3. The sums of all of these distances, sums of all of these distances, sums of all of these distances, and then we would add them together individually. What you can see from this picture is that despite the fact that these clusters are relatively small and they're very tightly packed, their particular inner terms are going to be very small because there aren't that many terms and all of the points in these clusters are very close. However, the downside of that is that this cluster over here has a lot of data points in it, and many of the data points are far away from the cluster center. So this picture over here is going to have a somewhat large measure of heterogeneity. These two clusterings over here are very close to one another. In general, we expect them to have a smaller heterogeneity than over here because we don't see as many large lines going out from the centers of the clusters to the observations in that cluster. However, when we compare these two pictures, the only real difference between the pictures are these two data points right here. And in the picture on the left, it appears that the lines connecting them to their cluster center over here are a little bit larger than their lines connecting them to the cluster center over here. So of these three clusterings, we would expect this one to be the least heterogeneous. And so this is the one we would want to return as the best clustering for this data. So this is a good method that helps us improve and make better choices about which clustering we choose to represent our data. However, the problem with this is that k-means can be a very expensive algorithm to run even once on large data sets. So thinking about trying to run k-means several times in order to get a more accurate result can be a little bit daunting. And so there are other things we can do to improve the accuracy of our k-means algorithm, which we will discuss next.